Dear students, welcome once again to the EduSat learning program. Today we are going to discuss about grouping of capacitors. In the previous class, we have seen how to calculate the charge on a capacitor, capacitance of a parallel plate capacitor with and without dielectric, the energy stored in a capacitor. Let us start with that point. If a capacitor of capacity C is charged with a potential V, then charge on the capacitor Q will be given as CV. The force between the plates Q square by 2A epsilon naught. The energy stored in the capacitor is half QV, Q square by 2C or half CV square. The electric field inside the capacitor between the plates E is a constant. Therefore, if we calculate the energy density, it is the energy per unit volume. So, this will give you half CV square divided by volume is A into D, putting the value of C as epsilon 0 A by D, you will get it is half epsilon 0 V by D square. V by D is nothing but your electric field, so it is half epsilon 0 E square. The energy density means the energy per unit volume. If you calculate in the electric field between the two plates of the capacitor, you will get half epsilon 0 E square. But the electric field is not constant for all type of electric fields. As we know that your electric field may be proportional to r to the power 1, proportional to r to the power 0, proportional to r to the power minus 1, r to the power minus 2, r to the power minus 3, r to the power minus 4 and so on. This is proportional to r to the power 0. This represents a constant or uniform electric field and that is existing inside a parallel plate capacitor. But for electric field depending on distance r, how to calculate the energy? For that, let us take an example. Suppose we have a charge Q at origin and there is a sphere of radius r. Let us imagine a sphere of radius r and we are going to calculate what is the amount of energy present beyond the circumference of this sphere. To calculate the amount of energy present beyond its circumference, we have to find out U equal to integration rho dV from r to infinity. So, integration rho is half epsilon naught E square as we have calculated and dV is the small volume I consider at a distance r from the charge with a thickness of dr. So, this will give me integration half epsilon 0 E square is Q square divided by 16 pi square epsilon 0 square r to the power 4 and dV is 4 pi r square dr. So, if I integrate this between the limits r to infinity, it is a very simple integration. It will be 1 by r square dr, it will be minus 1 by r, and when I put the limit, I will get simply it is Q square divided by 8 pi epsilon 0 square r So, the energy which is beyond R up to infinity will be q square divided by 8 pi epsilon 0 square R. Okay. So, in this way, if the electric field is non-uniform, we can calculate the energy in the electric field by using this formula. So, now let us discuss about the grouping of capacitors. There are two major grouping. Two capacitors may be grouped in series. It means the capacitors are connected one after the other. If we consider two capacitors of capacities C1 and C2 connected to a potential V, then this potential will be divided as V1 and V2, whereas the charge Q will be same for both the capacitors. So, therefore, for capacitors in series, same charge develops on each capacitor where potential is divided. This will give you Q by C, it is Q divided by C1 plus Q divided by C2. This implies 1 by C is 1 by C1 plus 1 by C2. If I extend to n number of capacitors, then the effective capacity will be given by summation I 1 divided by C I equal to 1 by C. So, we see here that the potential is divided, charge Q is constant. Now, to find the individual potential V1, we know Q is constant, Q equal to CV. So, CV is constant and V is inversely proportional to C. So, V1 is C2V divided by C1 plus C2 and V2 will be C1V divided by C1 plus C2. So, in this way we can calculate the individual voltages across each capacitor. Similarly, if I consider two capacitors in parallel, means they are at same potential, but the charges are divided. This is C1 and this is C2. Here V is constant, Q is divided. So, CV equal to C1V plus C2V. So, I get C equal to C1 plus C2. Therefore, extending to n number of capacitors, I get C equal to summation Ci I from 1 to n. It is the number of capacitors present in case of parallel grouping. Here, since Q is different, so I can write Q1 equal to C1V and Q2 equal to C2V. In terms of the total charge appearing on the capacitors, I can write here V is constant. V is constant means Q by C is constant or Q is directly proportional to C. So, Q1 is C1Q divided by C1 plus C2 and Q2 is C2Q divided by C1 plus C2. So, we can calculate the individual charges appearing on the capacitor by using this formula. This is about your series and parallel grouping. Let us consider a mixed grouping of capacitors. In a mixed grouping of capacitors, suppose I have a mixed grouping like this. B, this is my C, C and C. So, in this figure what we see that C1 and C2 are in parallel and this combination is in series with C3. So, therefore, C dash equal to C1 plus C2 and the effective capacity C will be given by 1 by C equal to 1 divided by C1 plus C2 plus 1 divided by C3. So, this implies C will be equal to C3 into C1 plus C2 divided by C1 plus C2 plus C3. Okay. So, in this way we can calculate the capacitance in a mixed grouping. In some cases, the capacitors in a group, they are whether in parallel or in series, we cannot understand clearly. To know about the connections among them, whether they are in series or in parallel, we can adopt some simple methods. For example, let us take a small example. Suppose 3 capacitors are connected like this. This is my P and this is my Q. These capacitors are all are having capacity C. In another figure, suppose this is my P and this is my Q. In another figure, suppose this is my P and this is my Q. Now, let us find the effective capacitance between P and Q in all these 3 figures. In figure number 1, to calculate, you see, we cannot say which one is series and which one is parallel directly looking at the figure, because the figures are distorted. And therefore, let us adopt a very simple method. Let us number the joints. These are the joints. Okay. Now, let us number the joints. Now, we know that a conductor is an equipotential surface. So, therefore, in the first figure 1 and 2 are at same potential. In the same figure 3 and 4 are also at the same potential. P is connected to 1 and Q is connected to 4. Between 1 and 3, I have a capacitor. Between 3 and 2, I have another capacitor, 3 and 2, and between 2 and 4, I have another capacitor. So, what we see that all the 3 capacitors are in parallel. So, therefore, the effective capacitance C equal to, or we can say C final equal to C plus C plus C, this is 3 times C. Similarly, in the second figure, again P is connected to point number 1, 2, 3 and 4 are at same potential and it is connected to Q. 1, 2, 1, 3 and 1, 4. There are 3 capacitors connected. So, all the capacitors are in parallel. So, C final is again equal to 3C. Similarly, in the third situation, here 1 and 3 are connected. So, 1 and 3 are at same potential, whereas 2 and 4 are at same potential. 1 is connected to P and 4 to Q. So, between 1 and 2 we get a capacitor, between 2 and 3 we get another capacitor, between 3 and 4 we get another capacitor. So, what we see, all are in parallel. So, the effective capacitance CF is again 3C in this case. Okay. There are so many other methods, we will see one by one. So, for just by looking at the figure we cannot say whether the capacitors are in parallel or not. We have to adopt some simple means to see whether they are parallel or in series. Now, let us expand our horizon to some complicated networks. If we consider 12 capacitors, each having capacity C connected on the sides of a cubical cage. Suppose there are 12 capacitors, each of capacitance C they are connected like this, and this is my P and this is my Q. Now, again we can use that potential point method to simplify this circuit. Let us number the junctions 1, 2, 3, 4, 5, 6, 7 and 8. Let us try to go from 1 to 8, because 1 is my entry point and 8 is my exit point. If I go from 1 to 8, I will have several paths like 1, 2, 6, 8, 1, 3, 5, 8 and 1, 4, 7, 8. You see, I may continue, but all the points are already plotted on the whiteboard. So, therefore, I should not continue or should not lose time. So, 1 is at a potential, 2, 3, 4 are at same potential, 5, 6, 7 are at same potential and 8 is at a constant potential. So, therefore, 1, 2, 3, 4, 5, 6, 7 and 8. This is my Q and this is my P. Now, let us connect the capacitors 1, 2, 1, 3, 1, 4, 2, 5, 2, 6, 2, 5, 2, 6, then 3, 5, 3, 7, 3, 5, 3, 7 and then 4, 6, 4, 7, 4, 6 and 4, 7, 5, 8, 6, 8 and 7, 8. So, we can see that it is simplified to a very simple circuit of parallel and series capacitors. So, this is my 6C, 3C and 3C and 6C. So, 1 by CF equal to 1 by 3C, 1 by 6C, 1 by 3C. So, 6C, 5. So, C final equal to 6 by 5C. So, this is my answer. The final capacity is 6 by 5C. Okay. Now, if my entry and exit points are different, then also we can use the same principle to find out the grouping, whether they are in series or parallel. So, you have to take different set of equipotential points. Suppose for an example, if my Q is here, suppose it is connected to 7. So, I have two sets 1, 3, 7, 1, 4, 7. This means 3, 4 are equal potential. Again 1, 2, 5, 8, 7, 1, 2, 5, 8, 7 and 1, 2, 6, 8, 7, 1, 2, 6, 8, 7. So, 5, 6 are at equal potential. So, I can have points like this 1, 3, 4, 7, 2, 5, 6, 8. This is my P, this is my Q. So, this is 1, 2, 1, 3, 1, 4, then 3, 5, 4, 6, 3, 5, 4, 6, 3, 7, 4, 7, 8, 7, 5, 8, 6, 8, 2, 5, 2, 6. Okay. So, there are 12 capacitors, now they are joined like this. Okay. Using another concept of balanced Wheatstone's bridge, we can calculate the effective capacity of this figure. We will see after some time what is a Wheatstone's bridge and how to calculate that. So, using this potential point method, we can simplify any complicated circuit available or coming to us. Now, let us discuss about an infinite ladder. If the capacitors are connected like a ladder what we use in our daily life, suppose capacitors are connected like this. So, this forms an infinite ladder. This is my P and this is my Q. Suppose each are having capacitance C. Now, we have to notice that which one is the step which is being repeated to give us this infinite ladder. We have to left one step to left and the rest other is assumed to have a capacity of x, because if it is an infinite ladder, then the step of this ladder is also infinity. So, if I detach one step, again it will remain as an infinite ladder. So, therefore, let the capacitance of this infinite ladder is x with one step left to that infinite ladder. Now, if I calculate the final capacity, because now this is reduced to a figure like this, P and Q, C, C, and this is my x. X is the capacity of infinite ladder with one step minus. So, the effective capacitance C again will be equal to x, because infinite plus 1 is also infinite. So, therefore, x is equal to how much? This x and C are in parallel. So, it is x plus C, and this one is in series. So, it is x plus C into C divided by x plus 2C. Now, cross multiplying, we get x square plus 2cx equal to xc plus c square. So, this will give us x square plus cx minus c square equal to 0. So, my x is minus b plus root over of b square minus 4ac divided by 2a. So, this will be equal to root 5 minus 1 by 2 into c. So, if all the capacitors are having same capacity. If not having same capacity, it is all right, C1, C2, C3 and whatever it may be, but you should notice the step which is being repeated. It is very important. So, noticing that step, you have to keep one step left and the rest is your x. Now, the entire is your x. So, equating the two and using or solving a quadratic equation, you can find the value of the effective capacity of an infinite ladder. So, now let us consider another form of capacitor which is commonly used in our daily life in radio tuner, as a radio tuner, TV tuner, etc. These capacitors are the gang capacitors. In gang capacitors, what we get? A large number of capacitor plates are so arranged that they are forming a gang of capacitors and giving us variable capacity. We will discuss about gang capacitors after some time. As discussed, a gang capacitor is consisting of large number of plates and those plates are connected. We have to trace whether the plates are connected in series or in parallel, that is very important. Now, let us take an example. Let us consider a gang capacitor having, suppose, plates like this. Now, if this capacitor is charged, then suppose this is my positive terminal and this is my negative terminal. In a positive terminal, I get a large number of capacitors, capacitor plates, as well as with the negative terminal also. Let us first develop the charges on these plates. Since this plate is connected to the positive terminal, this will be plus, this will be plus plus, plus plus and this is plus. And what we see, at least there are 1, 2, 3, 4, 5, 6 capacitors. Similarly, the negative charges are minus, 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 minus and minus. Okay. So, let us number the plates 1, 2, 3, 4, 5, 6, 7, 8. Now, my positive plate is having 1, 2, 3, 4, 5, 6, 7, 7 plates. 1, 2, 3, 4, 5, 6 and 7 plates. 1, there are 2 3s, 2 5s and 2 7s. Similarly, 1 2 is forming a capacitor, 3 2 is forming a capacitor, 3 4 is forming a capacitor, 5 4 is forming a capacitor, 6 5 or 5 6 is forming a capacitor, 7 6 is forming a capacitor and 7 8 is forming a capacitor. 2 4 6 8 all are connected to the negative terminal. So, clearly we see here that all the capacitors are in parallel. So, my effective capacity, final capacity of this Young capacitor will be 7 epsilon 0 A divided by D. If A is the area of each plate and D is the space between the plates, it is 7 epsilon 0 A by D. So, what we see? The plates are alternately connected and there are total number of 8 plates are there. So, in such situation, in general we can write it is n minus 1 epsilon 0 A by D. If the plates are alternately connected in a Young capacitor and n number of plates are there, then the effective capacity will be n minus 1 epsilon 0 A by D. But the thing will be different if we introduce a neutral plate between the two terminals or between the two plates. Like, now let us consider a Young capacitor like this. Suppose this is a Young capacitor, this is my positive terminal and this is my negative terminal. We can see clearly there is a neutral plate introduced between the inside the Young capacitor. So, this one will be plus, this is plus plus, this is minus and this is plus, this is minus, because the neutral in the neutral plate we will get bound charges as I have already told you, and this will come due to the polarization. So, equal amount of positive and negative charges will appear on the same plate on either side of the plate. So, if I suppose take a charge q here, then this will be my q by 3 and q by 3, and this is minus q, this is plus q, and this is minus q by 3, minus q by 3 and minus q by 3. If we calculate the charge on the neutral plate, we will say it is 0, because minus q by 3, minus q by 3, minus q by 3 is minus q and plus q, and that is equal to 0, and that has to be 0. Now, if I number the plates, then I get 1, 3, 3, 1, 3, 3. This is my positive plate. 1, 2, 3, 2 and 3, 4. These are the negative plates of the neutral plate, and the positive plate is 4, negative plate is 5. Now, the capacitors are connected like this. The middle section is the neutral plate. This is minus, 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 and this is plus. So, 3 capacitors are in parallel and one is in series. So, the effective capacity in this case, it is 3C or 3 epsilon 0 A by D and 1 in series. So, 3 by 4 epsilon 0 A by D. So, by dividing the charge and numbering the plates, we can see in a Young capacitor whether the capacitors are in series or in parallel. Okay. So, this is about our Young capacitor. Now, let us see what will happen if the capacitors are connected like this in the form of a bridge. This is called a bridge. So, between P and Q, suppose this is my C1, this is C2, this is C3, this is C4 and this is C5. This is known as Wheatstone's bridge for capacitors. The bridge is balanced if C1 by C3 equal to C2 by C4 or C1 by C2 equal to C3 by C4. The balanced condition means this is R and this is suppose S. Potential of R is equal to potential of S, implies is VRS, VR minus VS is equal to 0. If the potential difference between the point R and S is 0, we can say the bridge is balanced. So, this capacitor C5 will have no use in the network. If C5 will have no use in the network, then the bridge is now converted to a very simple series and parallel network. C1, C3, C2, C4 between P and Q. Now, first these two are in series, C2 and C4 are in series, then these two are in parallel. So, in case of a balanced bridge, it is very easy to calculate what is the effective capacity, and it can be easily converted into a series parallel combination. If the bridge is unbalanced, if the bridge will be unbalanced, then we can use Kirchhoff's law or delta star transformation or star delta transformation to simplify the circuit to series and parallel, and then we can solve for the result. Now, let us see if the bridge is not balanced. Let us start with a particular example. When the bridge is not balanced, then obviously C1 by C2 will be not equal to C3 by C4. Let this is my 1 microfarad capacitor, this is 1 microfarad, this is 1 microfarad, this is 1 microfarad and this is 2 microfarad. This circuit can be solved by using Kirchhoff's law and also by using delta star transformation. We will see one by one. Suppose we are going to solve it by using Kirchhoff's law. Kirchhoff's law is summation Q equal to 0 at any junction and summation E equal to summation Q by C in a closed mesh of battery and capacitor network. Now, here we have two meshes, and in those meshes, now let us try to develop the charges according to Kirchhoff's first law. Suppose I have a charge plus Q here coming from the battery, and this is my charge Q1 developed here. So, here is minus Q1, let the charge is Q2 here. So, this charge will be Q1 minus Q2, so that minus Q1 plus Q2 plus Q1 minus Q2 equal to 0. Similarly, on this side, if this is my Q1, so this will be Q minus Q1 and this is minus of Q minus Q1, and this plate will have a charge of minus Q2. So, this plate has a charge of Q minus Q1 plus Q2, Q minus Q1 plus Q2. So, this plate has a charge of minus of Q1 minus Q2, and this is Q minus Q1 plus Q2 minus. Now, if I add these two charges, this is minus Q1, this is plus Q1, they will cancel. This is minus Q2, this is plus Q2, they will cancel, and I will get a charge of minus Q. So, if a charge plus Q is entering and minus Q is exiting, so it means that the charge development is correct. And now, applying Kirchhoff's law in the first network, I will get Q1 by 1 C plus Q2 by C minus Q minus Q1 divided by C equal to 0, because there is no battery in this network. So, what we get? We get 2 Q1 plus Q2 equal to Q. This is my equation number 1. Similarly, in the second network, what we get? Minus Q2 by 1 plus Q1 minus Q2 divided by 1 minus Q minus Q1 plus Q2 divided by 2 equal to 0. So, it is minus 2 Q2 minus 2 Q2 minus Q2. So, minus 5 Q2, this is plus 2 Q1 and plus Q1. So, 3 Q1 equal to Q. This is my equation number 2. Now, multiplying 5 in equation 1 and adding with equation 2. So, equation 1 into 5 plus equation 2. This will give us 10 Q1 plus 3 Q1, 13 Q1, 5 Q2 minus 5 Q2, they will cancel, and 5 Q plus Q is 6 Q. So, I get Q1 equal to 6 by 13 Q and Q2 equal to Q minus 2 Q1, Q minus 2 Q1 is 1 by 13 Q. So, Q1 and Q2 are calculated. Now, let us consider this point is A, this point is B and this point is C. So, V AC will be equal to V AB plus V BC. If the total charge is Q and total capacity is C, so this is equal to V AB is Q1 by 1, but V BC is Q1 minus Q2 divided by 1. So, this is equal to 6 by 13 Q and Q1 minus Q2 is 5 by 13 Q. So, C final equal to 13 by 11 microfarad if all are 1 microfarad and 2 microfarad itself. So, this will be 13 by 12 microfarad. So, in this way you see, when we apply Kirchhoff's law, first we have to do charge division at any junction, and then we have to use the Kirchhoff's second law to find out the charges appearing on different capacitors. Then we use the potential division formula to find out the effective capacity. The same thing can be calculated by a simple transformation known as the delta star transformation. What is a delta star transformation? In this figure, actually this delta is creating a problem. Delta means this triangle. This triangle is creating a problem. If I can convert this triangle into a star, then that star will be connected to the vertices like this. So, if a delta C1, C2, C3 is converted to a star to be connected like this, then the capacitor connected between C1 and C2 will be C1 plus C2 plus C1 C2 by C3. Similarly, this one will be C2 plus C3 plus C2 C3 by C1, and this will be C1 plus C3 plus C1 C3 by C2. By using this concept of delta star transformation, now let us see or reduce this figure into a figure like this. This figure will be reduced to a figure like this, where This is C1, C2 and C3 all are having 1 microfarad capacity. So, it is 1 plus 1 plus 1, it is 3 microfarad, 3 microfarad and 3 microfarad, this is 1 and this is 2. Now, if I calculate or simplify this one, I will get this is 3 by 4 and this is 6 by 5. So, 3 by 4, 6 by 5 and you calculate it out, this will be 13 by 11 microfarad. So, very simple, using delta star transformation we can convert a very critical network into a very simple series and parallel network. We can also use a star delta transformation if some star is creating a problem, then we can convert it to a delta to make it a simple series parallel circuit. Okay. Now, let us see about the grouping of charged capacitors. We have a capacitor of capacitance C1 charged to a potential V1 and another capacitor C2 charged to a potential V2. Suppose this is the positive plate of the capacitor and this is negative plate and this is the positive plate and this is the negative plate. Now, the charge on the first capacitor Q1 equal to C1 V1 and charge on the second plate, second capacitor will be Q2 equal to C2 V2. If in this case we join these two capacitors, if we join these two capacitors, charges will flow from one to the other and after a common potential is established between the two, the flow of charge will cease. If we calculate the common potential and that common potential will be summation Q divided by summation C, because when they are attaining a common potential, they will be in parallel. So, this is equal to Q1 plus Q2, the total charge divided by C1 plus C2, or we write V equal to C1 V1 plus C2 V2 divided by C1 plus C2. But if we connect the plates of opposite polarity, then what will happen? If we connect the opposite polarity plate, then my V will be equal to C1 V1 minus C2 V2 divided by C1 plus C2, because when opposite polarity plates are connected, the charges will be cancelled. The net charge on the capacitor after connection will be Q1 minus Q2, but the effective capacity is same, because after attaining a constant potential, they will be in parallel. So, in one case we are getting it is C1 V1 plus C2 V2 by C1 plus C2 when same polarity plates are connected. When opposite polarity plates are connected, we are getting C1 V1 minus C2 V2 by C1 plus C2. So, now let us have a small question. Suppose a question is coming like this, these are two capacitors, this is my C1 potential V1, this is my C2 potential V2, this is my point A, this is point D and this is point B. If the capacitors are connected like this, then what is the common potential? Potential of D. The potential of D will be given by summation CV, means C1 V1 plus C2 V2 divided by C1 plus C2. This formula will give you the common potential, but in this case we can also calculate the energy before and energy after connection. Energy before connection, U initial will be half C1 V1 square plus half C2 V2 square. Energy final is half C1 plus C2 V square, where V is the common potential, and therefore, the loss is a loss in energy Ui minus Uf will be equal to half C1 C2 by C1 plus C2 into V1 minus V2 square. If two capacitors of capacities C1 and C2, potentials V1 and V2 are connected, then the loss in energy will be half C1 C2 by C1 plus C2 into V1 minus V2 square. Okay. So, let us evaluate some small problems. Suppose there is a linear chain of batteries and capacitors. This is a battery, this is a capacitor, and this is a battery, and this is a capacitor. This is my point number A and this is my point number B. This capacitor is suppose 1 microfarad and charge on it is suppose 2 microcoulomb, and this is 1 microfarad, charge is suppose 1 microcoulomb. This is suppose 6 volt and this is let me it is 12 volt. This is negative, this is positive. Okay. So, now suppose we are to find out the potential difference between A and B. To calculate the potential difference between A and B in this situation, what we have to do is, we are going from A. My potential is VA, then plus 6 volt minus Q by C, it is 1 volt minus 12 volt and again plus 1 volt equal to VB. So, VA minus VB will be equal to 13 equal to 6 volt. 13 minus 7, it is 6 volt. So, the potential difference between A and B, VA minus VB will be 6 volt. So, this is my answer. So, in this case, what we have done is, you see, the capacitors normally they are passive elements in a circuit. If we along the path, if we are encountering the positive plate of a capacitor, then it will drop your voltage. But if you are crossing the negative plate of a capacitor, then you will add up your voltage. Similarly, on the path, during the path, if you are encountering the negative plate of a battery, then it is charging you, and if you are encountering the positive plate of a battery, it is discharging you. So, using this concept, we can calculate the potential difference between 2 points in a battery capacitor network like this. Okay. So, this is the potential difference between A and B. So far we have discussed charges, charges properties, Coulomb's law, application of Coulomb's law, Gauss law, polarization of a dielectric, parallel plate capacitors, their grouping and simple applications. Thank you.